Hello, can you hear me now? Hey guys, looks I will be opening the session. There might be some hiccups with the registration process. Should I get some presenter capabilities?
Yeah, I'll give you a presentation rights in a moment. I'm just going to give it a few more minutes for people to turn up and do a quick intro and then hand over to you, if that's okay.
Oh yeah, sure.
Cool.
And maybe one more question. How are we going to show the slides?
So I've uploaded the slides already. I've taken them from Indico. So if you uploaded a new version since a few hours ago, then you'll need to upload again. Once I give you presenter rights, which I can do right now if you want to upload slides, you'll be able to upload a new version. Or is this version fine?
It should be fine.
Cool. So yes, as soon as you have the presenter rights,
Awesome.
you'll be able to click through the slides. Have you done this before? Did you attend one of the trainings or play about in a hack room?
Not really.
Okay, well, let me give it to you now. So once I give you presenter rights, there'll be a little plus in the bottom left-hand side of the media pane, and you can select which presentation and then just flick through them there. Let me do that now.
Sounds good to me.
So you should now be able to share your screen and or click through presentations and do polls and other stuff. And scribble on the slides. Okay.
Should I turn the presentation back to you somehow?
That's okay. I can do it.
Ah, awesome. Thanks, David.
Hello, welcome to day 3. Okay, my camera isn't working. Well, welcome to day 3 of Plumbers. Thank you for coming. We're going to give it a couple more minutes. People are still showing up. I'll try one more time to get my camera working. No camera, it seems. So, first things first, I'm going to run through the sponsors to say thank you. Without the sponsors, Plumbers couldn't happen. So thank you to Facebook, our diamond sponsor, to IBM, Microsoft, AWS, Netflix, and Red Hat. Thank you to Collabra for sponsoring the speaker gifts, which many of you will have received. And also to VMware for sponsoring the t-shirts. The t-shirts will be given out to the first people who respond to the survey, which I believe you've just received a link to in the email this morning. Since we're not in person, we're not giving out t-shirts with registration this year. And of course, to the Linux Foundation, who support everything we do here. We really couldn't do it without them. So thank you very much. You'll have seen the code of conduct numerous times already. I hope we don't have to remind you about that. And as ever, please keep yourself muted and your microphone off when you're not participating. But you can ask questions in chat. Depending on the presenter, they might want to be interrupted by turning your camera on to invite a heckle, or you can use the raise hand feature at the bottom right. But let's do what the presenter says, whether they want to be interrupted as they're presenting or whether they prefer you to wait till the end. So this is the planning committee, myself, the chair this year, Elena, Kate, James, Christian, John, Guy, and Stephen. If you need anything during the week, please don't hesitate to find us by email or in chat, or there's a help desk, various other methods. And no, we're not on a break. So I think with that, I'll hand over to Pavel. Are you also having problems with your video? I cannot see you. Is that just me?
I'm not sure.
I think it's just you.
I'm presenting it. It looks fine.
Okay, well, if everybody else can see you, thank you very much for being part of Plumbers, and I will hand over to you now, and then, oops, no, I'll hand over to somebody else. If people would just stop joining the room for a second, I'll make the right person presenter. There, try that. That's a suboptimal UI. Brilliant. Thank you very much.
Thank you. Thank you for the kind introduction. My name is Pavel, and I do not mind me being interrupted, so please raise your hands if you have something to say. So yeah, I'm working at Facebook, have been contributing to IOUing for a long enough time, and today I want to talk a little bit about our work in progress work on bringing BPF to have fully in-kernel control of IO using IOUing. So I believe there was enough of different articles and talks about IOUing, so I will just briefly outline the idea, and that's it. IOUing is a communication channel and new API which brings serves as a communication channel between the user space and the kernel space. There are two sides, so submission queue and completion queue. The user space, or just users, first fill one or more entries into the submission queue, where each entry represents some operation like a read or write. Previously, with synchronous operation, so with synchronous syscalls, it would be like just a normal syscall. Now it is enters in the submission queue one. Then when it's ready, it does a system call to actually submit all the I/O to the kernel, and then kernel do all the job on submitting request. When a request completes, it posts an event into the completion queue where the user space can grab them from, and there is all the needed different API like waiting on completion queue and so on. There's also a SKU poll mode, which I have to mention. It's where you have a kernel thread which actively polls the submission queue, and so in this mode, the user space usually doesn't even need to do any syscall. The kernel thread will just find it and submit on behalf of the user space. Yeah, we've got a lot of different request types, from basic read and write from the beginning to a bunch of different network operations, polling, splicing, brand new, just recently merged file system operation, and the list still grows. And we also got a lot of different features. Already mentioned SKU poll. Oops. Okay. Already mentioned SKU poll, IO poll for queueless IO. Different register resources, we can register files and buffers, cut some overhead on different ref counting, like file ref counting, or different internal accounting allocation, and so on. We've got a notion of links, which allows to just link a couple of requests together so they're executed in order, and by default there is no ordering in IO for the submitted operations. There is different optimization for execution flow, like internal polling and so on and so forth. And I want to give a little bit of an idea how we execute our requests. Okay, it looks like the slides are a bit outdated, and so I uploaded them like 2 hours ago. Anyway, so how do we execute our requests? We usually first try to execute them in some no-wait mode. And so they can just complete because there is already data for whatever reason it is, or can go async as it would be the case with, for example, direct block IO. If it doesn't work, we will try our best to find some asynchronous mean to execute the request. For example, for buffer trees that miss the cache, we can wait on a page, or for pullable files like sockets, we can try to execute polling internally and try again when the poll fires. So it's kind of hidden inside IO during epoll looping, but a bit different. But if nothing else works, we would fall back to a thread pool. It is usually slower than any other asynchronous mean, but often necessary. But for all hot paths, we try our best to avoid it. So, and because from time to time we see some people having some strange ideas and being absolutely sure in them, I was thinking it would be nice to leave the slide for the reference. The first misconception is quite popular, but say for some reason, I have to say it out loud. IO is not just a worker pool. As I said before, worker thread is a slower path, and we wouldn't have got such a performance with just worker pool. The second one is that IO is not IO completion ports. Not going to elaborate on that, but just to think about a funny fact that Microsoft now tries to bring an IO for Windows. Definitely it will be interesting to see where it goes. And at last, it's not only about syscall elimination, reducing the number of syscalls, the greatest benefit is the API itself, providing uniform way of doing asynchronous I/O, and also providing so many optimizations that haven't been available before. Okay, going back to the main topic. A problem is that the hardware vulnerabilities hit us hard, and all the mitigation made syscalls pretty expensive. And even though we have some syscall batching in IOing, it still takes some time for doing syscalls. And to give an idea, if you have some tight loop with syscalls inside doing not much work, for example, for this one, I've been doing like 4 kilobyte copy. The syscall overhead was taking for me more than 50% of CPU time, but for more or less newer and better CPU, I would expect it to be like maybe 20-ish, 30-ish%, something. Still a lot. And for the next case, I was using a standard IOing benchmark. In this instance, it was doing no op operations, but with batching 32, and that means that we have just one syscall per every 32 operations, and it was taking like a quarter of CPU. And with something more realistic, like I/O against a block device, null block device in this case, with somewhat more realistic batching with 4 requests at a time, it was more than 15% for me, which is still a lot. And this test was just doing like 1.6 milliamps per second. And if you have been following Jens's updates on IOing, he gets like 3.5 and more milliamps per core with a single open drive. So it's not so unrealistic case. I mentioned SQPoll before, and one may ask why not do not use SQPoll to just eliminate all the syscalls. But it's not really the ultimate solution because we have some problems with SQPoll. The first one, it requires a separate core, otherwise it is kind of useless probably. And it gets a lot of, takes a lot of CPU cycles. You can get cache bounce, and you still need the user space to process your SQs, and it would probably need to wait for completion. So it's kind of depends on your workload, but it may still be a syscall for waiting. And so, following the whole idea of throwing BPF at every problem we have, let's try out BPF here as well. Okay, there are some requirements we put up. The first one would be flexibility, because basically the user should be able to program anything they wish with it, and if there are too much restrictions, it would be just useless piece of junk, yet another one. So the first one, BPF should be able to submit new requests. That's obvious one. And as it submits new requests, we should also be able to access the results of them, having some kind of feedback. More to that, we may want to access multiple completions at single BPF run. Another criteria would be to be able to analyze and access normal user space memory. Of course, there are always some BPF's way of doing it, like maybe using BPF maps, BPF arrays, but it can be a problem for adoption, especially if the application have never used BPF before. And the other criteria would be it should be of low overhead, otherwise the user can just go to the user space and that's it. So the first idea of using it, a dump idea, is to add a callback for each SQE and run it for each request and run it on completion. And fairly enough, it could be of benefit for some cases, but I see just more problems to it. First of all, it adds some overhead in the generic non-BPF path. And not only that, but it also prevents some further optimizations, and that's a big no. And also, we should be able to finally control the context from which we executed, because it shouldn't be run from RQ. We may need to avoid recursion and all this stuff. And this code just looks horrible. Yeah. The way it's solved is just creating a new IOUring type of requests, BPF request, which basically solves all the problem I mentioned and nicely give us a way to use all the IOUring internal infrastructure, all the batching, all the optimizations inside. There are also a bunch of nice wins, like being able to wait and so on. The only downside to it is that it may require, it's not free. It adds some overhead, but we can work with it, and more about it a bit later. The next problem was to get completion into BPF program. So we could have used linking, the first idea that came to mind, but it has never been considered seriously because it is by design pretty limited. So the idea is that we can use links and we can pass SQ of the previous request to our BPF program. But as I said, first it by design binds it to linking, which is already pretty restricted. And also there will be a problem to passing multiple CQs, and that's a bummer. The way we did go is by creating multiple completion queues, and each request just specifies submission times to which completion queues the completion should go, and obviously BPF will be able to get events from any completion queue, post new events, and so on. It also gave us one nice way of new synchronization, like posting to another completion queue. And for example, what I had in mind of using it, for example, you have some bunch of work and let's say a piece of work, and you create a BPF request, you allocate a completion queue, gives this completion queue in use to this BPF request. So the only one using this completion queue is that BPF request. You run this BPF it, keeps itself alive working on the problem, and when it's done, if ever, it just posts a new completion or using any other way of notification to the user space that it's done with the work. The last one was about accessing the user space memory, and it is actually already solved by BPF. They introduced not so long ago sleepable BPF programs, and that solved a lot of problems. And that's a big deal for using BPF as well, because submission may want to wait. So it's quite a hard requirement for us. So about the overhead, some may want to, the first thing, some may want to use a lot of BPF requests, and it costs some time because some may link additional BPF requests per each normal BPF request, basically doubling the number of requests. As you may guess, it would cost you something. And the other problem is that we usually were optimizing it for batched submissions because there is a system called constant overhead. So submitting just by one request doesn't make too much sense for IOURI from the performance perspective. But good news, we did a lot of work on that front past year. We cut a lot of just overhead number of instructions for submitting requests. We amortized some parts of per submission overhead. So for BPF, it is pretty much free. We did a lot of different optimizations like request caching and other kind of batching, completion batching, all the stuff. So it's not really too much of overhead for creating an empty request, especially comparing to overhead we have down the stack, for example, for doing actual I/O. So a little bit about the API. First of all, you create your BPF programs. It's not as interesting here, it's BPF specific. Then you register your BPF request in IOURI. You can unregister them as well. There was proposal to have not registered BPF requests, so it may see the light at some point. This slide would be just an optional optimization. Next, to submit a BPF request, you as usually just fill in an ASCII entry, submission queue entry. You specify the opcode to be BPF, and you set the program index, which was registered before, and that's it. From the BPF point of view, first of all, just a reminder that BPF programs take a context argument, which you see as the struct in the middle of the slide, and a BPF request usually can return some return code. So if it specifies return 0, it just instructs the IOURI to complete the request, the BPF request. If it returns wait, prior to that, it should fill into entries in BPF context to specify for which completion queue it should wait and for how much request it should wait for. There is also user data in BPF context. It's basically the user data you specified when you submitted the BPF requests, and if it just treat it provide some additional way to provide some context to BPF programs. And at the bottom, there are basic BPF helpers to submit new requests, emit and grab CQs from completion queues. Pretty basic and all as I described before. Here is a lead BPF example with maybe useless but showing all the API which I described before, getting new events, submitting new requests, reading user space memory, waiting for completion queue. And there are some further ideas what we may have, what we may want, and it may see the light at some point, depends on where it goes. But if you have some ideas, it would be welcome. We would love to hear it. So going to the numbers. There was a group of German researchers who were willing to try out the project. And so big kudos to them. They proposed one test case, which I'll be describing here. It is a big file copy with buffer trees, and the file is fully cached. So maybe nothing interesting, but it kind of gives an idea about overheads and what we can get. As you see, if you take a look at the first table, you can compare the first line and the third one. With mitigation enable on one setup, we've got like 40% win for BPF or something like that. But when we disable mitigations, during BPF pretty much loses to the synchronous version, which is pretty much expected. And that's great to get such a performance win with mitigations enabled. But it highly depends on the CPU. So we tried out another one, and for another CPU, the difference is not as great as it was for the first tests. You can see in the second table that the difference is not as big as before. So it will be highly dependent on mitigations you enable and on the actual CPU you use. It might be not so interesting examples, but that's the one I put here, and other cases are still in development because each of them requires some optimization and some thinking of it. So it's left for further updates. Excuse me. There is some parts missing in the slides, so we'll just talk through it. I have to note that I do not expect it to be pretty much useful for applications which naturally have a good batching rates and do not care much about latency, but it's not always the case because first of all, batching usually hurts latency, and the other one is that it's not always possible. For example, with sockets, TCP sockets, you would need to serialize it somehow at the end because of ordering concerns. And Excuse me, give me a second. Yep, there's a lot of different ideas. I would love to try it out for caching system databases, for broadcasting collect. Some people mentioned before Quick, using that it can benefit by using it in Quick protocol, and there is some move on those fronts. Did I lose that?
Just trying to switch you over to the latest version of your slides.
Oh. Okay. Can I get to the previous one? Perfect.
Is that the one?
Yeah. So there are some cases we would love to try a more realistic one that would benefit in the real world, but and there are some motion on that front, but it is not quite still there. It would be also interesting to see if it would be of use the fuse file system. But if you have some more ideas, again, we would just love to hear them. Next steps would be to explore new test cases and do optimizations, and each new test case usually brings some ways to us to optimize a thing. And it was to do it because it usually benefits normal IO ring, non-PPF IO ring as well. So it's a good exercise for us. Yeah, and there are some backlog left, some stuff on BPF side, and some slight regressions because of multi-CQ, which I need to solve first. And that's it. There is some resources if you would love to go through. The BPF stuff with liburing and examples, and just our IUring mailing list guides and manuals.
That's great. Thank you, Pavel. So does anybody have questions? Raise your hand or turn your microphone on or just speak up or ask in the chat and we can relay. Well, I think you have explained it all extremely coherently there. I'm looking forward to playing with this a little bit for Open Connect, but yes, in my copious spare time, I will come and have a look. Thank you very much.
Okay, thanks a lot.
Thank you. Hi, Alex. We'll get started in a few minutes. Do you want to? I've just given you presenter rights. Do you want to just have a quick look at your slides and make sure you've got the right version?
I just sent you a couple, during the last session, I sent you the, for sure, latest version.
I have attempted to convert those to PDF and upload them for you. Do you want to have a look and make sure we've got it right between us?
Sure. PDF. Maybe I should share my screen just. What I think.
Up to you. So I've uploaded the PDF, but you can share your screen if you prefer.
I do. So let me just try it out. One sec. Funny. One and one code needs to be granted. Where do I grant you? Oh, okay. 1 second. I need to. It's Mac, so I need to provide. Now. Hi, back again. Maybe. 1 second. Yep. Let me just see if everything works as expected. Yep. So animations kind of work. Big one. Yeah. David, how does it look?
Looks good, thank you. So we'll give people a few more minutes to roll in, and we'll get started. Thanks.
The zoom on this. by the way, I have issues with the matrix chat. So if there are questions posted on the chat, I will not see them.
Okay, thanks. I'll try and relay them for you. So it is, well, 3 o'clock GMT. We should be starting in a moment. We'll probably give it another couple of minutes for the stragglers to roll in. So how do you want to do questions? Would you like to be interrupted during the talk with people sort of turning their camera on and waiting to be called on, or would you rather they wait?
I left in enough space in the talk for have interruptions. Well, let's allow people to have their questions, and I want to see how the crowd interacts and feels about the talk. So yeah, so let's have it in line.
Okay, cool. So you can raise your hand by clicking the little hand icon at the bottom right-hand corner of the media screen, or you can just turn your camera on and wait to be called on. And yes, I will attempt to relay questions from the chat if anybody doesn't notice the fact that you said you can't see it. Hello, I have a child. Yes, you may. Welcome back to the Refereed Track. Thank you everybody for being here, and thank you Alex from VMware, who is going to make the case for memory segmentation. And off you go.
Hi folks. So this is a combination. I want to share actually 2 projects that I've been involved in a couple of last years, and one is regards to security, and one is regarding performance. And surprisingly, the solution is kind of the same. It shares the same benefits, and the solution is memory segmentation. And so, well, I'll start. So basically, memory segmentation solves these 2 issues. So one of is DMA security, when you don't want an attached device to take over your machine. And actually, this work was presented at a system operating system conference in 2018. And my current project involves rethinking zero-copy networking. Right? So I presented this talk at NetDev just about a month ago, and you can find the the full-fledged talk and slides on YouTube and on the NetDev conference page. So then, DMA-aware malware for networking. Why do we need this? I'll start from the beginning. I will assume no one knows anything, so but I'll try to be quick about it. So DMA, direct memory access, is when you have this, DMA DIM, and you have attached devices like NVMe, GPUs, and NICs, obviously, that can write directly to this to your memory without involving CPU, which obviously is good for performance, but can lead to DMA attacks. And you have a couple of notorious examples like this thin firewire unit, which was discovered a couple of years ago in a WikiLeaks leaks. And you have this PCI leech project on GitHub. So basically, in all of these cases, you have some machine, and that is attached to your, well, in this example, laptop, but can be your server or whatever you have that does compute and supports DMA. And it can actually hack your machine, take over. So luckily, we have IMU. So IMU provides other specializations, like just MMU for processes. That's the same benefit you get from an IMU for devices. So to 6 device access only to those pages that the operating system defines. So you have a virtual address for the CPU accessible pages, and the IO virtual address that the device can use to access the memory, right? So it has its own translation tables, just like process. Now, I'll get into the send operation just to make it more clear. So when you send a buffer, right, the device driver, what it does, it gets the virtual address of the buffer, DMA maps, and then it allocates in IOVA, the process, the DMA map operation. It allocates in IOVA. It updates the device's page table, right? So we have the IOV according to the physical address of the page. And then the packet is sent, right? So when it gets into it, reads the address, the IOTLB. That will be just the same as a TLB for process. So we have a fast locus head cache for devices as well. So IOTLB is updated, and then you have to daemon map. Right? You must revoke the access to this page because there's no need for the device to have access to this memory. So we remove the page level entry, and we must flush the IOTLB, otherwise the device can still access the memory, although the page table has no record of this. Right, and then we free the actual IOV address. So that's how IMU, DMA API, and device drivers work together. I hope made it clear. Now, the problem with IMU, besides the fact that it really kills your performance, that it doesn't actually provide security, which is kind of, would be nice to have. And the problem that it has is called a subpage vulnerability. So in this case, the device driver needs to, the device needs to read only just one small bucket, like an ICMD packet or R packet, or something small, right? It needs access to just a single cache line, but it gains access to the whole 4K page, right? And furthermore, when you think about, if I'm being specific about, network devices, on the receive side, what happens is that each time when you receive a packet, right, and it can be 1,500 bytes, you actually expose a structure that's called estimation info, and it appears in every I/O buffer that is going on the receive packet, right? And this can be shared info includes a couple pointer or a pointer to a couple pointer, which can be overwritten, and things go bad from there. Now, following the, people understood this and kind of talked about it, but then finally in 2019, this project Thunderground came in, and what is shown that they can take this feature and take, just one of the things they did is take the E1000 emulation from the Intel device driver that is used for visualization, plug in the FPGA, make it malicious, and actually take over your purpose and your working machine. And they did it for Macs, Windows. They kind of did a poor job doing for Linux, but for that we have this master thesis by buffer that show that Linux is also vulnerable to subpage vulnerabilities. So basically, if you have a physical machine that anyone can somehow get physical access to, today it is vulnerable, right? Because IMU doesn't provide security. So this is a problem that we set out to solve in 2000, well, actually 16. How do you provide a DMA security to your system and still don't lose all of the performance benefits from high-speed networking device, right? Because we know when you use strict protection, when you invalidate the ITB each IO, you can really go more than a couple of gigabits per second, and your whole CPU is just busy doing the IoT implementation. So how do you provide both security and performance? That's kind of the question. And what we understood then that the API itself, or actually the security assumption that we have of the DMA API, as we saw it, is incorrect, right? So we have the DMA map, and then the device has legal access, and then we have the DMA unmapped, and then the device has no longer has a actual access, and it doesn't provide the security because of subpage vulnerability, because in that window of time you can still have metadata that is accessible, and while in this valid access time slot, the device can do malicious stuff. So you don't have security, and maybe you don't need these borders. Maybe they are artificial. So let's see what happens if we relax these restrictions, right? So we allow the device to access the buffer any other time. So that's kind of the slide that I described. So when you do the mapping for and mapping for each buffer, you either have the cost of map and map, or there was also a solution that actually also was one of our projects, which was presented in 2016, where we actually, at the point of the map and map, we just allocate a different buffer, which is constantly mapped and copied between the two. And kind of worked fine until you went up to 100 gigabits per second or more, and then your memory control was just short. So you have to do work each time. You have to add some transient state to the state that you're working with, and there's no way around it unless you relax this assumption that the DMA map that the API provides is security. So we changed the API semantics. Now the idea is when you receive a buffer, and we're talking about receive because on send you have read access, which is dangerous, but not as dangerous as write access. So on receive, you have this buffer and you DMA map. And at this point, you just do nothing because you don't really care if the buffer is mutable, or it's not until the information is accessed by the CPU. And when the information is read, this is the point in time we must provide security. And actually what happens is for most socket APIs, right? You receive a buffer and the headers are read. So the first cache line is accessed. Maybe the first two cache lines are accessed. But the whole, the rest of the 1500 bytes are just untouched most of the time. So when we copy, when the POSIX system call copies the data from the kernel to the user, you get your immutability of the data, which is what you need, right? So when the CPU reads, you just disallow any more changes to the buffer. So the way we did it, we revised network socket. So revise is a strong word. Basically, I looked for any memory allocations for buffers, for IO buffers, and replaced them with a specific different allocation called, which allocated buffers that are always DMA mapped. So we have a pool of pages that only have an IoT apps, either read or write access, and it's a pool. The pool is implemented with magazines. It's my favorite. I'll talk about it maybe at the end. So there's an allocator that you can ask to get a page which is already DMA mapped. You don't have to map it on your own in the data. So that's what DMA aware malloc for networking is. So when you do this, your mapping and unmapping operations both do nothing. Well, the mapping operation actually returns the IDVA which you need to, but it's already there. It's already part of the page itself. And so you allocate a specific allocation function, but you don't really care about the freeing part because that's taking care of the free page and break free and whatever. The standard memory arrangement in the next term, right? So reference counting, and which is 0, at this point actually goes back to your DMA aware malloc rather than the page. Right, and you can release some memory via the shriek interface in other ways. So, question?
Yeah, allocated for mapped for which device?
That's you have the context for in TCP socket, and actually in the UDP socket you allocate memory. You already know which device is this buffer is intended for. So you have this context and you can get it. So for receive and transmit as well.
Don't you have to do routing before you know which device you're going to transmit?
The point that's kind of the interesting. So sockets, TCP sockets, obviously they are connected to the device, and you already know where it goes. UDP, it happens to be the case as well that when you get to the point in the code where you allocate memory for I/O, you already know which device you're going to use.
Okay.
So we did for TCP and UDP, and that's kind of, we covered 99% of the networking needs. Control path from the kernel, it's like you don't really care about it. It's just so low volume of networking, and SCPP and others, DCCP will find someone who uses, and we can provide a solution to that as well. So that's kind of the idea of memory segmentation. So you have this memory that has its role, right? And it is used for IO, right? And it's never used for anything else. And as David put in, for IO for a specific device. So it can have multiple mail, then pools, each for each device. Obviously, there are limitations for secure zero copy and zero copy operations like file send and rerouting from one device to the other. So there are limitations. And there are obviously stupid things that the device drivers can do, where just put metadata on the IOV map page, and then you don't really achieve anything. So because it's not a talk about DNS security, I kind of put all the links for the previous projects, the papers, and there's also a YouTube video where I talk about the vulnerabilities and provide some tools that can find in static analysis and dynamic analysis the vulnerability in your kernel. So if you wish to read about it, there's the list. Thundercloud project is the one project that I was not associated with, so that's why it's got its own green color, but it's a cool one. And yeah. So if you're interested, this is the list. So this is kind of the place to ask questions, because now I want to talk about my current project and the one I'm really excited about. So can I give you a couple of seconds for questions, any? Okay, so mail. In this case, we leave security behind. It's a new context. In this case, we're trying to think about how to provide zero copy net. So all the solutions that we have today are poor, and kind of the picture as I see it today is you kind of have two choices. When you build an application, you can have your sockets, and then you just, it's simple as this. It's a high school programming project. You just import a socket, create a socket, connect to the destination, and send your hello world, and you're happy. And the other option you have is account backups, where you hire a team of highly skilled engineers that work for weeks and months, and things then do blow up. And the reason why you're making this choice is because one is fast and the other is slow. So how do we bridge this gap? So obviously we want zero copy. That's kind of the main, the holy grail, because system call batching and everything is in the works. You can do it with IOUing, for example, as we heard in previous call today. But zero copy for networking is the holy grail. So the problem with zero copy for networking, as opposed to storage GPUs, and now it's because the packet arrival order is random. You don't really know where the next packet is going, right? To which user. So in this case, the kernel must provide its own generic memory. The packet arrives, and then the data is copied to the correct process, right? And on storage and GPUs, what you have, for each IO who requested stuff, right? So the process asks for an IO, provided it's usually a bigger buffer than the networking buffers, and it provides these buffers. And when it turns from this specific buffer, user provided buffer is used for IO, data arrives, and we have zero copy. And this is a problem for networking. So what are the challenges? So kind of it's isolation, isolation, and isolation. So first and foremost, you have to isolate the kernel memory from the user. You can't ever allow the user to access any memory that is currently used or was previously used by the kernel. And you want to, in the data path itself, so as we talk about them, so probably the first cache line of the network packet will usually be accessed. and you don't really want to allow the user to be able to modify the headers in flight because IP tables and forwarding and stuff. You don't really want to open this thread idea anyhow. And obviously you have to isolate one user from the other, right? So now we're talking about different security concerns that have nothing to do with DNS, right? So in the last 40 years, so we had this kind of a bunch of solutions for zero copy. First, we have dynamic mapping, something that Eric is doing, and Google so have message zero copy, TCP MAP, and it kind of it's not free, right? You have this page table manipulation in data path, so you still pay the cost and actually some trouble for to scale almost the cost. FreeBSD had an attempt to do copy on write, but as far as I know, it's dead now. The second thing that people do is kernel backups, which is nice. So you have DPDK and FXDP current that had NetMap 10 years ago and probably more, and it's kind of cool. You get zero copy, but you lose all the network stuff. You don't have the protocols. Obviously, you don't have TCP, UDP. You don't have the routing, anything. You need to do it all on your own, and it's kind of a shame. So Linux has 30 years this year, and there's a lot of networking work done, and some kind of a shame to lose. The next thing that people can do is provide limited use case solutions. So we have splice, send file, submap, so a lot of things now with eBPFs. But none of this is a generic send receive that you would like as the atomic constituents of your application, right? So you want to create a buffer, do some work, and send it and receive. You don't want to mess with files or anything else, and besides, it's not cheap as well. And obviously, we have specialized hardware, right? So RDMA, and we have a couple of families of protocols like IWAP, InfiniBand, Rocket, which are all great. Right? The problem is you need to have the hardware end-to-end. You need the RDMA-aware switches, RDMA-aware NICs, and probably in the future, and the future was around about 20 years ago, and still don't come RDMA-aware routers, right? And kind of the last thing that people think about is shared memory. And I actually looked about, and I couldn't really find any interesting or solution on projects that actually survived their initial presentation. And to my mind, this is kind of the right way to go. So the reason why shared memory was not accepted is because of the isolation issues that we discovered. So in shared memory, you can't really easily make sure that the kernel is not subject to some persona, unless you do memory segmentation. And so that's kind of the solution. So you provide IO only pages, and have pages that have a specific role to do IO. And in there we actually saw caches for device. Well, you can actually apply the same logic to user space. You can have IO caches for user space pages. Right? So in this case, you would take a mail page and you send it for IO. So kernel device driver will allocate an IO page. The packet arrives, and then it's delivered to the process, to the correct process. So how does this happen? So kind of similar to maybe questions after the slide. So first thing first, to have isolation. So kernel memory. So no kernel data is ever located in an IO page, ever. Not before, not after. Everything that is written to this page is something by the user or for the user. Right? So the kernel memory is secure. Isolation between processes, right? So you have the random access, the random arrival problem that we talked about. So, but there is hardware support to solve this. So NVIDIA, previously known as, have the notion of qubits. That's how they implement a DPDK buffer for drivers. That's how RDMA works, and it's the same API is used for Ethernet as well. And basically, which means you can create a context pair process. It'll have a simple syntax called ADQ, and obviously you can emulate something and do virtualized power drivers in others. So if some hardware support, you can isolate the process, the between process. And now about the control path, well, we have scatter guard receive, where you can do header splits, and I think all new vendors do that. Mellanox included. So you can make sure that the first cache line is in non-user accessible page, and the rest of the data is. Right? So here we go. You have shared memory, but you have none of the isolation problems, and you achieve it by just segmenting the memory. And it's kind of the same idea with them. It's actually the same solution. That's how I actually thought about this one. Just flip the script. No. So obviously, I want to talk about more about zero-copy semantics. Limitations of zero-copy. So zero-copy semantics are not the same as copy semantics. I'll pause a second because if people had questions about isolation, is it the right time to ask? No. Okay. Here a pause. Right. So zero-copy semantics versus copy semantics. So what happens is that when you do I/O with zero-copy, your buffers change ownership. When you do TX, the buffer is no longer yours; it belongs to the kernel. On receive, you don't have actually support for serialization and unitization of your data. You just provide 64K and say, "Hey, put my information here in a single stream." You will actually have to deal with scatter data received, and you're probably limited to the size of NTU or whatever Harvard Java support there is on the device. And so now with Mayo, the pictures that we had this API, you create a socket, you connect, and you send, and now you have this API. Well, so it's somewhat more complex, but not that much. So first thing, we have to create your Mayo cache, so your memory allocation for our cache. So what I'm doing here is this specific implementation. I'm using compound pages. So first thing, for performance, it's best to use huge pages, and kind of it's kind of a question why 2 megabyte pages are not the default, and then you have big pages for 1 gigabyte and small pages for 4K. That's kind of the way to go in the future, but it's kind of the next steps. So compound pages is when you have a bunch of memory pages that you can treat as one. Right? So there's a data structure we actually create. I'm getting ahead of myself. So you initialize huge page memory for the process, and you do it in any way which you would like to do it, and you create your allocate. Right? So in this example, just a cache of 4K pages and 60K pages. This implementation. And then we create a connected socket. So the sockets that I'm using in this implementation, and again, I'm saying this implementation because once you have memorization, you have this notion, you can actually do it in a bunch of places. So once we got over the hump of understanding, okay, we actually segment the way of how we segment the memory dynamically, and then let your imagination run wild. So this is a specific implementation of this memory segmentation for zero-copy. Obviously, it helps to understand the difference. So we initialize your memory, we create a socket. So in this case, I'm using kernel socket. It's a system call, which I provide this essentially destination IP import, and a kind of default of the other flags, and because it's a book and not really a full-fledged API yet. Right? So we create a connected socket. It's a TCP socket, and now we have a kernel TCP socket, and we have an identifier. It's like a file descriptor, but it's separate from the file descriptor system. And then we allocate a buffer from that page to create. Right? So create a cache, and we allocate the page from this cache. We do some preparation, whatever, and send page later. So next thing we do, we initialize PTCP. It's basically like IOUing, then we send. So have a shared memory and ring buffer. You put your I on it, and you know, batch your TX or receive operations. And then you send your buffer. So you provide the index of the socket, the buffer that you want to send, the length of the buffer, and some flags. And it's usually a more flag. Do you have more buffers to send? Do you want to have a system call that will send it immediately, or do you have more IO to go behind it? And then some time later, you probably want to inquire about the state of the page. Has the kernel finished doing its TX operation, and then you can use your page. So that's the new API that I propose, and it's kind of well, basically I love it, but it's my approach. So what is memory segmentation specifically I want to talk about again? So it's memory that is intended for a single specific use. Right? For DMA, those IVA map pages. For mail, it's user space shared pages. And you allocate when you dedicate allocate in the kernel, in the user, wherever you're using it. But you don't really need to worry about freeing. So that's why you can push it up the network stack and don't worry about or whatever. Once the reference count reaches 0, the packet returns to your specific cache. And so the things that we need to change is kind of in the core of things. It's structured page, but not structure page itself. I just need to add some fields, and it actually doesn't make struct page grow, right? Because adding fields to a compound page, to the first tail page of the compound pages. If you're not familiar, I will with the compound pages. I will just wait for the next slide. I will talk more about it. So there is, surprisingly, more things that you can stuff into structure. And then you just have to modify get and put page and compound head, because in the case of compound pages, you have a huge page, a 2 megabyte page, but for IO, I'm actually using each 4K setup. So compound head needs to be modified as well. And pageref should never, ever be used in the kernel unless you know what you're doing. It kind of leads a lot of problems and MLX drivers. Just stop thoughts. Just stop. So pageref is a bad idea because maybe it's a compound page for some allocation just like this, and getting the wrong atomic reference. So what is the justification for getting functions like put page and get page? It's for every IO, for every memory buffer that is ever used. But we already do that, right? So we have put page, that's kind of the whole function. And we have def page buffer. We have specific use case for specific def page. Well, what I'm saying is that this line should be more generic. And so just have your callback and modify it, and it should be part of the page. And the way, for example, the way we identify mail pages is if it's a compound page and we have a specific field that I've added that is non-zero. And you can add your own checks and say that is this a dev map page, right? Thank you. So we're doing it already. We already have custom management of specific memory pages. What I'm saying is let's make it more generic. Now, so May uses to make huge pages, as I mentioned, and the first tail page, right? So compound pages have struct page, and one of the unions is this struct. Right? So in struct page, for compound pages, you will just have an array of struct pages, and so you have the head page, which holds a reference counter, and then you have all the rest of the pages that we are called tail pages. And the first tail page holds some information. And what we found is that you actually can put more information. So in this case, we have U address. So the first tail page has the user space address for the specific process that we're servicing. You can put the user space address of this 2 megabyte page And then you can do some other things like provide sub-compounding. Like we have 2 megabit page, but for I we wanted a 32K page. So this is the LM order for our mail pages. And actually, there's more things that you can do. So compounding hours, then one log of compound order. More information can be stuck in here. And I'm talking about, so actually, if you think about it, you can probably merge the solution for them and for zero copy. And then zero copy itself, well, you have to be compromised on security, just like you do with PK, but you don't compromise the system. And it's kind of really important. And you can have your address and the IRV in the same page and as a property of this page. It's not the transient which you update on each IO. It's permanent. And then you don't actually pay the cost of setting this transient property in runtime twice, one you start and then when you finish. It's exactly more than zero copy, it's zero overhead. So kind of the next steps for Mayo specifically, and probably then, is I want to send an RFC in a couple of weeks and let you guys think about it and say mean things to me. And obviously the user space library for Mayo. And Mayo is just beginning. So we can actually dethrone SRE. We don't really need SRE in a sense, not at least for branding. So because QEMU, for example, is just another process. So you can do nested mail, right? So you have the hypervisor that supports mail, the QEMU supports mail, and the guest OS that supports mail. So what you can get is, you have multiple queues, and then you have an application that uses mail. The PDK, for example, can use mail, and then you have QEMU, it runs a guest OS, and it has a guest application, and the whole stack is network aware. You can do zero copy with zero overhead, both on receive and feeds for guest OS. So obviously you'll pay the price in latency, but not in bandwidth. The next thing that we can do is actually, I was once asked, can we bridge the gap of zero copy and non-zero? And it's not trivial, but maybe we can mitigate some of the costs. So when doing copying in user space, you can actually do vector operations. And now we have, x86 with 6 nano channels and much wider channel. So maybe we can pay less in cycles to move very bytes around. Less, we can do faster user space. So if you have a mail backend and a non-mail aware application that just shares its own memory with the mail backend rather than the kernel, you can do the copy in user space. And then you can hopefully, I still need to prove and check if it works. You can actually do this, have the same application and do some LDP load and use mail operations as a backend instead of doing the system calls directly, and maybe get faster or cheaper I operations. That's kind of the three main things that I'm looking to do in the future. Right. So the basic premise here is memory segmentation, and I hope I was able to convince some folks, is just assign a role, which is not transient, to a page. Allocate it intentionally, and don't worry about freeing, and don't do stupid things that are on it. Like don't do metadata, and don't store metadata on an IO page. And then you can get secure IO at more than 100 bits%, which you couldn't do before. Else, your other option is do what we did previously, right? Add and remove the transit properties for each buffer. And then you can use IMU as we do today and have no security. So I will repeat it for the first project. As we use IMU today, in the strict option, when we flash the identity on each IO, the kernel is not secure. Right? So we have no security. It's like the naked thing. We feel like we have security, but we don't. Anyway, zero copy, again, it's the first true zero copy project which allows you to use all the network infrastructure that we built in the past 30 years and have this in the same application, right? Where you don't have to build the infrastructure all on your own. So if you wish, you can try the existing code on this GitHub. So my user on GitHub is just my family name, Makuza. If you have questions, just email me. I will be really excited if there are more people get involved, and of course, at least show support. And yep. So 40 minutes, 5 minutes for questions. I have more backup slides if we have questions about performance and specific implementation of the function, or even an example of really stupid things they can do with iron. David?
Thank you very much. There had been a question in chat about upstreaming, but I think you've covered that with the link you gave at the end. Does anybody else have?
It's my working branch, so the actual RFC patches are coming in the next couple of weeks, maybe a month.
Beautiful, thank you. Can you see the chat now?
No, sorry, I really can't. The metrics just spins and spins.
Fair enough. So anybody who is talking in the chat, if you have a question, please turn your camera on and ask, or ask me specifically, and I can relay it.
Okay, so let me just some to talk about performance. So this is some of the slides that I've showed. Basically, we run some experiments on GCP because we didn't have a physical setup when I started working on this. So basically, we took 2K buffers, each 16K, and we sent them in a loop over TCP, over one core. And what we got is that with an unoptimized solution, because the way I'm sending today is I'm using send page for each page rather than the whole chunk once. And so it's unoptimized, and it's not the best way to do it. Because message zero copy just does the one function call, and I do it 16 times for 16 buffers. And still with this really basic implementation, we get 8% faster than message zero copy, right? And you can see that looking at that perf, that may have just do TCP send pages, do the post, the system function, calls the speed send pages, and then just write and send buffer. There are no overhead actually, so it's overhead free. And while the message zero copy has a lot of page table manipulation stuff, and again, so I look at 16 cores doing the same. It's really had problem. It's the scale, right? The implementation details, I will not talk about it now because we're almost out of time. But if anyone is interested, you can look at the slides and read it on yourself, by yourself. And there is a DPDK version of Mail already because it's kind of my employer needed. Why? Because it's hardware agnostic. You have just one PMD Pullman driver for any hardware that you can tweak and modify to allow zero copy. And you still use standard Linux tools, and you can use hybrid use cases. Like you can use DPDK to decrypt the information, right, or encrypt it, and then send the plain text via the network stuff. And everything is basically zero copies. Kernel, user, back to kernel. And you don't pay any overheads, and you do encryption and decryption with vector operations in user space, which are optimized. And so simple, just have a receiver in addition to a stream, and do directly stream package the same way this packaging does. And they already have a huge page management and everything. I see Goop.
Oh, I just say I have looked at the proof status you have mentioned in the last slide, and I see a lot of focus on the spin local low pace. Seems it's a very high contention in that scenario. Is that right?
For which one of them?
You in your last slide, you show us
that was message zero copy. Yes, they had contention
yeah.
on
It's a contention. And can you give us the slide that you have show us that that the perf record report? Yeah.
Yeah, so skip the slides. Yeah, that's
yeah, it's here. And yeah, and it seems it's the most cost is on the queen spin local slow pace, and that means it's got a lot of got a lot of contention. What's happening? Do you think about it?
It's message zero copy. It's kind of I wanted to look at the scale issues. I think it's probably the same here. It's a virtual machine, and so maybe we have some issues with virtualization as well. Really, I don't know, and it's kind of that's not my project. That was not my focus. I don't really have good answers to why the basis message zero copy has performance issues. My focus was here on mail.
Okay, so you recorded that in the virtual machine, and so the recorder just represent the counting is at that point, but maybe they have released the CPU to the whole system. Yeah, that's right. It's
so the figure that I've shown kind of been slow down here. So because we were looking at hyper and Mayo and some native implementation, we just open a socket and start pushing bytes. What we did, we just captured the idle cycles. Trying to capture busy cycles is a mistake because undercounts when the system is busy. And what we look for is how many CPU cycles you're spending per cent byte. Because while Mayo message zero copy and send file we're reaching 32 gigabits per second, Hyper and naive stuck at about 20. So the way to compare them in a single graph is to show the number of cycles on average you spend for send time. So that's what we see here. So Hyper has got the sending test and Mayo and message zero copy are done on average to less than 2.5 CPU cycles. I'm sorry, for each send file. So the cost is there. Again, it's not a deep analysis. It's a simple experiment. And again, it's a work in progress. Thank you.
Okay, thank you. Yeah.
Well, I'm done again. There's one amusing thing I would like to show, but it's non-mandatory. If there are no more questions. Let me show the example really quick. So one really interesting thing you can do with the drive. So this is an NVMe fiber channel you need to test, right? So we have this Broadcom interface, for example. It's a generic driver. And what we do here, what they're doing in the driver is they create an event to the device, allowing the device read access to this command IU. Its size is 96 bytes. And a couple lines later, they map the response IU. Its size is 32 bytes and provide write access. So write access doesn't provide you read access. You can actually write, but you can read what you did. But when you look at the command IU and response IU, you actually find that they probably sit on the same page because they're part of the same data structure. So when they mapped one for read and the other for write, they kind of hope that they just map just 96 bytes and then 32 bytes. But what happened is they mapped this whole data structure and the one before it, by the way. And one of the things that they mount is FCP request data structure. And if you look at FCP request, we find it has a callback point, and which is basically which others which can then modify, right? And so when you talk about NXB and KSLR, nothing is actually panacea. It can be working on. And when you have this, both read and write access, you can plan for. So if you take an FPGA and instead of saying that I'm an E1000 device, you can say I'm an NVMe device. Let's start talking. Your Linux machine design. So that's why copying is also a solution besides that. So it's kind of all the free projects kind of should be combined. David, I'm done with the material. If no more questions, thank you all for the time.
Cool. Thank you ever so much, Alex. It's brilliant to hear from you. It's really interesting. And well, thank you again. So we'll start again in about 10 minutes for the next session. Hi, Anita. I uploaded your slides a few hours ago in my morning. Have you changed them since then? Or will those be correct?
I have not changed them since like 12 hours ago or something.
12 hours. Yeah, that's I did it since then. So yeah, I downloaded them from Indico.
Okay.
Yeah.
Thank you.
My morning, 7 hours ago. Thank you. Hello, welcome. Thank you very much for presenting, Anita. And thank you to Facebook for sponsoring, and to our other sponsors. Other sponsors are also available. So I think we'll give people a minute or so to roll in. It's just past the hour. And let you go. Are you okay to switch the presentation over? You just did that, didn't you?
Yes. No.
Okay, no problem. Let me switch it. So if you click the plus in the bottom.
I see.
That's it.
Thank you.
I will give the presenter rights back to you so you can switch pages. There you go. Cool. Well, welcome to Linux Plumbers Conf, and thank you very much.
Are we waiting another minute, or should I go ahead?
I think we should go ahead. Thank you very much.
Okay.
I think they've stopped coming in.
Nice. Okay, hello everyone. My name's Anita Zhang. I'm a software engineer at Facebook, and technically I'm on the containers team, but my primary work revolves around supporting systemd at Facebook. Today I'll be talking about how Facebook simplified and adapted UMD, our user space out of memory killer, into a new daemon that's now part of the systemd project, systemd UMD. My presentation is not very long, so I prefer to get through the slides first and address any questions at the end. There will be slide numbers on every slide, and you can also just drop stuff in the chat and I'll see it afterwards. Okay, here's the agenda for this talk. I'll briefly go over what is UMD and talk a bit about the background around the original UMD daemon from Facebook. Then I'll discuss what changes we made to adapt it for the systemd project in order to get systemd UMD. I'll follow that up with the current Fedora settings and how adoption has resulted in improvements for systemd UMD. And finally, I'll talk about future plans before opening the floor for discussion. So an overview of UMD. I'd like to reiterate that this is the original Facebook UMD and not yet the one that's part of the systemd project that I'll discuss in the next section. So my slides should be available for download if you'd like to check out the links later. Here I've included a link to the original UMD that Facebook open sourced on GitHub, as well as a link to Daniel Shu's 2019 LPC talk on UMD, if you're interested in more of the details around why Facebook developed UMD and how it works. But to summarize, UMD operates in user space, and one of its goals is to free up resources before the kernel killer kicks in. We want this because the kernel can spend an unbounded amount of time swapping pages and evicting the page cache when it does an kill. Some other advantages over the kernel killer include a more flexible configuration, which results in more deterministic kills. And I'll talk about that more in later slides. The kernel operates on per process related numbers, which are not the most intuitive from a user's perspective to configure. And kernel-based kills don't always translate to making user space healthy because the kernel killer exists to protect the kernel health. As for the technologies driving UMD, it operates only on cgroup 2, and one of the big things it uses is pressure stall information, or PSI, to make killing decisions. I mentioned that the kernel killer operates at a process level, and so its configuration is process-based, but UMD only operates at the cgroups level. UMD's cgroup-centric model was chosen due to the advantages with resource control. With cgroup 2, you can group processes together and set various resource limits on them, as well as get accounting metrics. And as part of these metrics, you also get PSI for each cgroup. Usually when I mention a pressure threshold or pressure limit in this talk, I'm referring to memory pressure from a cgroup's PSI file. The PSI metrics show what percentage of tasks in the cgroup were delayed due to lack of resources. So for UMD, the threshold or limit values correspond to what percentage of tasks in the C group couldn't make progress due to lack of memory. I'm glossing over a lot of the detail for the purposes of this talk, but I've linked to one of the Facebook microsites which explains this better. Here's a snippet of what an UMD configuration looks like. It's written in JSON, and you can tell it things like what plugin to use, which C groups to monitor, and what thresholds to act on. And the continuation of that is what the action format looks like. In other words, what plugin to use when a kill needs to happen and which C groups to operate on. So integrating this into systemd. Why systemd UMD? In some ways, it's something that was naturally going to happen due to the fact that UMD is tightly coupled with systemd. A lot of our current configuration relies on systemd C group setup and how it organizes the C groups hierarchy. And UMD relies on systemd C group knobs to set up things like the memory controller. Besides that, systemd as a user space component is well positioned to interface between the kernel and applications. And the systemd project is generally receptive to making novel use of resource control. But at the end of the day, we want to make it easier for people to adopt user space killing, and shipping UMD and systemd is one of the best ways to do so. Systemd is widely adopted, so it would make UMD available without any additional installation or dependency burdens. And by conforming to systemd's syntax format, it makes it easier on users to configure limits for themselves. As part of the integration with systemd, we had to rewrite UMD in C because systemd's daemons and the project are primarily written in C, while UMD is C++. And then the other hurdle we had to deal with was the interface. Stylistically, systemd's configuration is very limited as it uses INI style syntax, so plain text sections of key and value strings. JSON that you saw in the UMD configuration is not acceptable. And the idea of having arbitrary plugins was also discouraged during initial discussions with the systemd maintainers. Since not everyone has a resource control team like Facebook to tune UMD, we wanted to make it as easy as possible to adopt user space killing by removing some of the complexity around picking parameters for UMD, but also balancing it with an interface that could become too inflexible to be useful. Since Facebook had been running UMD in production for some years now, we narrowed down the initial version of systemd UMD to two core stable features: memory pressure-based kills and swap-based kills. For memory pressure, systemd UMD watches for pressure that exceeds a supply threshold and kills a C group based on the page scan rate. We've had different kill decisions and plugins for pressure-based killing in the past. However, page scan from a C group's memory.stat file best reflected which C group is the largest consumer, while taking into account any memory protections that are in place. Swap-based killing is the most straightforward, I think. If swap use goes above a supply threshold, then systemd UMD picks the C group to kill based on swap usage from memory.swap.current. In Facebook direction, we tend to over-provision swap, and so if swap gets depleted, it's a good indicator that there's a memory leak or other anomaly. Here's an example of what the daemon configuration looks like for systemd UMD. This exists primarily to set up system-wide defaults, such as the swap use limit, and what defaults to use for memory pressure-based killing if they're not set in the unit configuration. The unit configuration is where you actually decide which C groups to monitor and kill. And for the rest of this talk, I'll likely be using unit and C group interchangeably, since every unit in systemd has a corresponding C group. And here's an example of what a unit file looks like to enable killing with systemd UMD. By default, managed swap and managed memory pressure are set to auto. which means this C group on the slide, burb.slice, won't be monitored for swap or memory pressure-based killing. Only when these things are set to kill will systemd oomd monitor and kill things. There also exists managed preference, which can be set to tell systemd oomd to deprioritize or ignore this C group if it's included as a candidate during kill selection. More on kill selection in the next slide. Don't worry about reading the super tiny text. I'll explain it in a bit. You might have noticed that another big difference between oomd's JSON configuration and systemd oomd's unit-based configuration is that you no longer explicitly state which C groups to monitor or kill. oomd's configuration allows you to do something quite interesting, which is monitor one C group, but kill a C group in an unrelated subtree. Normally, no one does that, but it's an interesting quirk. Systemd oomd's configuration does not allow you to do this. Monitoring in systemd oomd is tied to the managed settings in the unit. And so killing is tied to all the leaf C group nodes under that monitored unit. So in the example on this slide, the dark orange boxes, alpha.slice, bravo.service, and charlie.scope, all have managed memory pressure set to kill. That's what's written in the small text. So systemd oomd will monitor these C groups and kill things under them if they exceed their set pressure limits. I've circled the possible kill candidates on the slide. So from left to right, C group Foxtrot is bravo.service's only leaf node. So if bravo.service exceeds its threshold, that's the only C group systemd oomd would kill. Charlie.scope has no children C groups, so nothing would be killed if Charlie.scope exceeded its thresholds. That's one quirk about this setup. You wouldn't want to set something like managed memory pressure kill on a unit that doesn't actually have sub C groups below it. Alpha.slice has two leaf C group nodes. However, in the small print inside echo.slice, I wrote that policy is set to kill. This is a systemd property that sets the C group file memory.oom.c group to 1 and tells the kernel killer to kill the whole C group if it kills a process inside it. Systemd oomd does something kind of similar when it sees this. Instead of going all the way to the leaf node, systemd oomd will stop at echo.slice and potentially kill it and all C groups below it. In this case, echo.slice and golf.slice, golf.service. So outcomes from starting in Fedora 34, systemd oomd became the default user space killer. And as a starting point, we had to ship a default policy for Fedora and settled on watching for memory pressure on the user manager C group going above 50% for 20 seconds and watching for swap use limit on the system going over 90%. This would cover all things started by the user, with swap covering the rest of the system. One of the big concerns around shipping systemd oomd by default was around systems that don't support an organized user C group 2 hierarchy. For example, GNOME is nice as it splits all these starred applications into their own user services. If you don't do that, you could end up in a situation where a bunch of processes are under the same C group, and systemd oomd could wipe out too many things at once. We left it up to the individual Fedora spins in that case to opt out of systemd oomd if they wanted to. But since systemd oomd is a systemd service, people could also just stop and mask the unit themselves if they wanted to opt out. So killing is one of those things where people don't really say anything unless it's broken. And then even if it's working correctly, people might bring something up anyways. But we did address several things along the way. For example, the policy that we ended up shipping generally works well, but it didn't always go this way the first time. Initially, we had something much lower, like a 5 or 10% pressure limit on the user manager. This worked okay on systems with SSDs and swap on ZRAM, but it proved to be much too low overall. so hence we've bumped that up to 50%. Some other things that changed along the way: swap kills initially ignored how much memory was available and just focused on how much swap was available and whether there were large consumers of swap. This worked fine in our production fleet due to the over-provisioned swap, but for Fedora users, this kind of produced mixed results. I think due to using swap on ZRAM by default and having less swap overall, this tended to keep more things in swap even when memory was free. So that behavior has been updated now, so that we only kill when both memory and swap usage are high. And then there's an issue with high CPU usage. Systemd UMD runs with a timed loop, and initially it would read memory.stat from a C group every iteration for every leaf node that was a possible candidate. And it was doing this to record the page scan values. However, reading memory.stat across that many C groups ended up using like 3% of CPU. So that behavior has been updated now as well to only read memory.stat for the moderate C groups and to get the information for the rest of the kill candidates when the pressure limit is hit. Future plans. So this slide's pretty short, but likely more features will be coming to Systemd UMD and Systemd as well, as we continue to migrate more of our hosts from UMD to Systemd UMD. But one of the primary limitations for desktops is that the initial implementation of Systemd UMD only applies to system units. That is, any user units with managed settings are ignored by Systemd UMD. This generally worked fine for server workloads, but it's not ideal for desktops. I think ideally we could set different limits on a user's app.slice, which runs most applications, compared to like session.slice, which holds more of the critical user services. I've linked a PR that is now merged in order to support this. Another thing is silent kills. Generally, when an kill happens, either in the kernel or Systemd UMD, you don't really get a lot of notice about it. The application just kind of disappears. So you go into your logs and you'll get the log line about what killed it, and maybe you'll make some sense about it. But it would be nice to get more visible feedback about why an application was killed or when it gets killed, maybe a pop-up or a desktop notification. And we have an issue open right now discussing this kind of thing as well. Okay, thanks for listening. I've had a lot of support in getting Systemd UMD to where it is now. And of course, this list of people is non-exhaustive. But now I'll take questions and open the floor for discussion.
Thank you, Anita. You can see the chat, can't you? So I think there are some questions there. Do people want to turn the microphone on and ask?
I can start. I have just really two very short questions, and I already pasted them in the chat. Thanks for the talk. That was really interesting. I hadn't followed the OMD development recently. This is single threaded and standalone, so it's, I guess, a separate binary in the Systemd tool suite, right? Again.
Yes.
Okay, cool. And this second one is whether this is already or is going to make use of cgroup.kill when it kills C groups. Like how? This is a new feature that is upcoming in cgroup v2, where you can directly kill a C group by writing into a single file, essentially, instead of, I guess, what you're doing right now is iterating through the C group and killing every individual task. Yeah. Okay.
Mm-hmm. Yeah. So I think we actually switched some of the Systemd code to use cgroup.kill. So Systemd UMD uses the same library Systemd does. So I think if we switched over what I think is the cgroup recursive killing function to cgroup.kill, Systemd UMD would have picked up that change already, cool. Possibly by the next version, but I need to double check. And actually, I should correct my statement about it being standalone, because there is somewhat of a hard dependency on systemd in that, we have to send the unit information over from systemd to systemd UMD.
Okay, so you essentially need dbus calls, right?
It's actually using the varlink protocol
yeah,
now.
right. That's the
But
new.
yeah, I
Okay,
made
yeah, yes.
dbus.
Yeah. Okay, cool. Thank you.
Would anyone else in chat like to ask their question? I can also read it live.
Let me ask. I think I already asked. So one thing is the C group V2 dependency. I think it might be more on the PSI side. But what else do you need? The OMD needs from the C group V2. Why there is a hard dependency on this V2?
I mean, Facebook kind of is like all in on C groups too. So most of our fleet at this point is not running C groups 1 at all. So it wasn't prioritized. But I think PSI is C groups 2 only. I need to check that statement.
So there is anything else in the V2 which is required for OMD?
Not required per se, but just the layout of the C groups 2 hierarchy is a lot easier to process, I guess. It makes the code a lot simpler as well.
Okay.
So no, nothing hard required as far as I know. Tom Ramatka asked, does this mean standalone UMD is now deprecated and no longer being maintained? So we are still maintaining UMD at this point. I think we do want to head in a direction where the main killing portions will be in systemd UMD, because despite the name UMD actually does things besides kill C groups. We use it internally for some monitoring things, and I believe Senpai is in a separate repo in GitHub, but we use that internally with UMD. So not deprecated yet, or at least not, for a while.
So I have one question more, not just on the on the systemd part, but more on the OMD part. So currently OMD, I am assuming it does mainly how the memory and the CPU guarantees are provided to the OMD when the system is under memory pressure. I can understand the CPU with the high scheduling priority and the memory, the mlock and stuff. One specific question, if you know, is more for the allocations on the syscalls and stuff. Whenever it has to read files, it has to read the stats and stuff. There are allocations there. It has to send the signals. So for in your production, have you seen OMD getting stuck in the reclaim?
So we have, I believe it's memory.low set on UMD. So at least from a memory side, it should always be guaranteed some amount of memory. But I don't know specifics about when UMD would get stuck. Actually, I've left my email on these slides if you'd like me to follow up on a question. You can also send me an email about it and I can get back to you. Let's see. Jordan Ugla asked, is there any graphical indication for desktop users that an kill has happened? So I addressed that in the future plans and kind of in another slide, but not right now. I think we may get something in GNOME in the future. That's what this, there's some discussion on this link here about that. But no, right now there's no graphical indication. Would anyone? Oh, hi. Oh, sorry, Vlast Timil, I think you're muted, or at least I can't hear you. I mean, you were unmuted before, but I couldn't hear you. I don't know why. Maybe it's me.
No, I cannot hear either, even when you are not muted. The mute icon goes away, but there's still no noise.
Oh, I can hear you now.
That's me.
Yes. There's a question from Mikhail about slide 14. Oops. Let's see. Does systemd UMD distinguish sub-C groups below .service level, or does it take .service as an atomic entity? Oh, let's see. So in this example, every sub-C group, even if it's created by systemd or not, it would be considered its own like a separate C group leaf node. Is that what you're asking? It's not, it doesn't look at just bravo.service by itself unless it's for monitoring purposes. For killing, it goes just below. If there are more C groups here, it would traverse each one to the leaf.
Can you hear me now?
Yes.
Okay, thanks. Sorry, I don't know what I just reconnected and it works. I had a question. There was a slide about the simplification for systemd, and there was that the memory pressure was based on PG scan rate. Does it mean that you no longer use the PSI in the systemd OMD version?
So PSI is used for the monitoring part. So we use PSI to watch when the pressure thresholds change. But when we kill, we sort by PG scan rate, and then we pick what to kill based on that.
Oh, so just for sorting. Okay. And thanks. And my other question, so it was always one of the issues with Linux desktops or laptops that they would, when the memory got exhausted, they would start trashing, and the kernel OOM wouldn't kick soon enough, and people would just reboot. So do you think that the system, the OMD, solved this for once and all? And
I don't want to make any claims about like for once and for all, but the specific situation you're talking about, UMD and systemd UMD both resolve live locks. Maybe not as quickly as you'd like it to. You can adjust the time threshold for that. But yes, it does fix these system live locks.
and there are no downsides, like in some situations it would kill too soon once you tuned the thresholds.
Yeah, so threshold tuning is, it's just like 1%. I mean, I think it does change a bit between what your hardware situation and swap setup is like on your system. But I mean, once you configure it, it's just all based on what's coming in through the PSI. It won't kill like more or less than what the PSI says.
Okay, thank you.
So one question I have is the action like UMD currently the action it does is killing, right? I'm wondering if you have or Facebook has looked more into the other potential action, for example, throttling or freezing. Like when there is memory pressure, maybe it makes sense instead of killing low priority, long running jobs, so that so they don't lose their work by killing them. Instead, throttle them or freeze them. Have you looked in that direction?
So not exactly that direction. Maybe something similar. We're considering like pre-kill hooks. I believe UMD does something like that already, or at least the one we're using internally. Systemd UMD does not support pre-kill hooks yet, but I'd assume you'd be able to like do notifications or maybe like debus notifications or send different signals or something before the sig kill happens.
So mainly the application has to add the support to react on those notifications.
Yeah. Let's see, going back to Mikkel's question. So he asked if Foxtrot had a sibling, would Systemd UMD treat them separately? So the nice thing about C group 2 and the Systemd hierarchy is that you can only have processes in the leaf node. So yes, Systemd UMD would traverse these C groups down, but it would only kill the leaf process if it had one, which has the processes. And then Systemd itself would probably clean up the remaining C groups since they're empty. But in terms of actually setting like managed memory pressure on Foxtrot, which is a service created C group and not a Systemd created C group, Systemd UMD does not respect that at the moment. Are there any other questions? I'm glad there's a bit of discussion going on about V1 and V2 in the chat.
Thank you very much, Anita. Yeah, trying to draw the line between when does the official presentation and the questions end and when has it sort of degenerate? Well, is degenerated the right word? When has it moved into the follow-on discussions? So I think I'll call it there. Thank you ever so much for presenting. It's been really interesting.
No
and
problems.
the chat will continue. Thank you.
Yeah. Thanks for listening, everyone.
Hello, Gabrielle, Daniel. I uploaded your slides for you probably about 10 hours ago, having downloaded them from Indico. Are they going to be the current ones, or have you updated them since then?
I wait for
Hello.
Libra to say. Yeah.
Hello. Hi.
Hello.
Yeah. Hi. Hi. Hi, David. Actually, I fixed the agenda because there was a wrong ballot. So.
Okay. If I give you presenter status now, you will be able to upload a new version of the slides. Is that okay?
Yeah. That is. I mean, I already did that. So that is.
Oh, you've already done it. Oh, perfect.
Yeah. So just to say that it's not exactly the same as 10 hours ago. It's just the agenda slide. Apart from that, everything is the same.
Where did you upload to the regular system or to Big Blue Button?
I uploaded to the to the
LPC
web,
site?
to the LPC site. Yes.
Okay, no, I can upload it here. I already downloaded a new version.
Okay.
I'll take the
Yeah, they also need to be loaded explicitly into Big Blue Button, which is what I was talking about. I'll let you do that then. Thank you. And we'll get started in about 5 minutes. Thanks.
Can I switch these slides already?
Pardon?
Is it a problem if I already switch the slides to the one?
No, not at all. Not at all.
Okay. No. Gabriele, you now have the control over the slides.
Okay. Okay, so great. Perfect. So let me know when we can start.
I would say now.
No, okay, good. Okay, so thank you everybody. So myself, Gabriele Paoloni. I work for Red Hat as an open source technical leader. I also am the chairman of ELISA governing board. And today I will present together with Daniel, also working on Red Hat as a principal engineer and Linux maintainer. And the reason why we are here is because we would like to have a discussion to present you an architectural model that we presented in ELISA in the last workshop, and we want to have feedbacks from a wider audience. Okay. Okay, so today here we'll present a maintainable, scalable, and verifiable software architectural design model for the Linux kernel. Okay. Some disclaimer. So this is a work in progress, and there are no results that are binding on behalf of ELISA or the Linux Foundation, and we don't make any safety claim based on this preliminary report. Agenda. So for first we'll say what is in scope and out of scope of this presentation. Then we will look into possible functional safety qualification approaches for Linux. Then we will go into the core of this presentation. So we will present this tailored architectural model. We'll look into a specific example, the iOctal, and then we will see how this model can be verified through the runtime verification monitors. That is what Daniel has been working on in the last few months, I think. And then we will look at the next steps and we'll take questions and answers. Okay. Okay, so what is the scope? We will, as I said, so we will present a proposal about high-level description and architectural design, and that is suitable, to meet ISO 26262 requirements. We will talk about software verification methodology associated with the architectural model. We will not talk about the overall FUSA qualification strategy for Linux, and we will not touch on any standard, any safety standard that is beyond ISO 26262. That is the safety standard that is used for automotive. Okay, so what are the options that we have today to qualify a pre-existing software component to be used into a safety critical system? Okay, and in this case, the Linux kernel is our pre-existing software component. So today, as of today, we have part 8.12 that is a black box approach, and it is based on verifying the software component top level specification. Okay, so basically you define the top level nominal and safety requirement, and you derive a comprehensive test campaign, and then you can say that this software component is qualified to be used in a functional safety system. Okay, now this is only accepted today for for software component of reduced complexity, and whose behavior indeed can be comprehensively described by the top level specifications. Okay, then we have part 6 that is a white box approach, and it is modular hierarchical. Okay, And this is suitable to develop and assess software component of any complexity, really. Okay, so there are no limits. Indeed, because it is a white box approach. And then we have part 8.14, that is the proven in use. Okay, so basically, if we have, if there is enough statistical data about failure in time of the software component under qualification, and if the software component usage condition are identical or very common to those that are used to collect the statistical data, then you can say that the software component is qualified according to the proven in use argumentation. Okay. And then there is part 10.9, that is the software element out of context. This doesn't provide any guidance in practice, because it would just, in the end, it redirects to the qualification routes that we talked about already. Okay. So today, we will not talk about the proven in use, so it is out of scope. The architectural design approach that we'll present, it's based on part 8.12 and part 6 together. Okay. Okay, so as already said, part 8.12 is pretty simple. We have the safety and nominal requirement, the pre-existing code. We have a requirement-based testing campaign, and there is no architecture required. Okay, so just a high-level description of the safety and nominal requirements. Okay, indeed, it's understandable that the amount of artifacts and collaterals to maintain in this case is pretty low. Okay. On the flip side, when we go and look into the part 6 standard approach, we can see that there are quite few activities that are involved. Okay, so we start from the safety concept, then we have the safety and nominal requirement, we have the software architectural design, the unit testing, implementation, the unit design, implementation, then unit test, integration test, platform test, and validation test. And following this approach, to assess a software component that was not developed according to part 6, it can be, pretty painful and would require a huge amount of rework, especially if we go down, if we look from the unit design below. So the effort, it can explode really. Okay. So now, as I said, the possible approach for Linux, given this overview. So, part 8.12 alone is not applicable because Linux is too complex. Part 6 can be applied. However, it's quite challenging with respect to the amount of work required. Part 8.14 is applicable, the proven in use, but there must be statistical data. Okay, so and the usage condition must be similar to those where the statistical data was collected. Okay, so as I said, for today, the 8.14 is out of scope. Okay. Okay, so problem is Linux is too complex for 8.12, part 6 is too complex for Linux. What do we do? So this is basically what we proposed. Okay, so basically down from the technical safety concept down to the software architectural design, the idea is to follow part 6. And then the single units that in part 6 usually are the single functions would be replaced by bigger units, really. And the idea was to start with driver subsystems, okay? And then, so the idea would be to qualify the single driver subsystems according to part 8.12, And then when it comes to the software architectural design and integration testing and above, we will follow part 6, okay? So in practice, when it comes to an architectural model to describe this, to support this approach, what happens is that we have the Linux kernel, so where we have a very simplified and a realistic view on the right. Okay, so the Linux kernel would be partitioned into macro block, right? That could be driver and subsystems, at least to start with. Okay, and each of these block is a software unit. For each software unit, the design specification can be described, can be defined using natural language, effectively using the kernel doc headers. And when it comes to the interactions between the different blocks, there will be a semi-formal or formal notation, okay? A semi-formal notation is basically a UML diagram, for example, okay? And so the idea is that, so to formally or semi-formally describe the interaction between the macro blocks and to describe the behavior of the single blocks using the natural language, so leveraging the kernel doc headers. Now, we talked about partitioning, okay, but then indeed the problem is what is the criteria to make this partitioning, okay? So how can we say, okay, this software unit is simple enough, okay, to be described using the kernel doc headers, right? And so if we look into part 8.12, that is the route that should be followed to qualify the single block, it is required that the specification of the software component must be described in terms of known safety requirements, known functional requirements, behavior in case of failure, resource usage, description of required and provided interfaces and shared resources, and configuration description, okay? So if you're able to specify comprehensively in natural language all of the specs above for a single block, for a single unit, then the level of granularity is the right one. Okay, so as you know, most of you probably, so maintainers already provide a sort of a view of Linux partitioning, okay, and can be used as a starting point, okay, to have a partitioning of Linux, and plus the maintainers are human, okay, so that will make it easy to map the single blocks to also to the people that are responsible for them, okay, and well, if we figure out that, okay, a certain subsystem or driver is too complex, then there is nothing preventing, you know, to divide it further, okay? And you know, it would be quite trivial, you know, to maintain a new partitioning file, to be honest, okay? So that is not the problem, really. Now, let's look into a specific example to better explain what we mean, okay? So this example is taken from the work that we've been doing in ELISA, okay? And one of the safety critical functionality that we analyzed is the capability of Linux to set the timeout of a watchdog using an ioctl. Okay, and so this is, so with respect to this feature, okay, our top level safety requirement is, you know, the watchdog subsystem shall ensure the watchdog timeout to be set according to the octal input parameter. Okay. Then, considering these requirements, we looked that, so the first input entry point is the octal itself. Okay. Then, okay, we analyzed the octal, the subsystem associated to the octal, that is the VFS. And you can see that from the maintainer file that we have the granularity here. Okay, so the maintainer file is exactly saying what are the files that belong to this block. Okay. Accordingly to the ioctal use case, we identified the subsystems and drivers that, in the context of the ioctal, the VFS communicate with, and this is a communication diagram that we derived. Okay, so you can see that there are some subsystems that are abstract, like the Arch subsystem. So in our case, we consider it x86. Then we have the security subsystem, the watchdog device driver subsystem, the work queue subsystem, and there are some functions that do not belong to any subsystem right now. Okay, so but as we said, maintainer is a starting point. Okay, the key concept here is that, so the communication diagram provides a static view of the relationships between the target software unit, that here is VFS, and all the others one that it communicates with. Also, what we did, we built a flow diagram that is hardly readable, but basically it will provide a view of the dynamic behavior following an ioctal of the file systems in interacting with the other subsystems and drivers, and also responding, to events, right? And the communication diagram, together with this flow diagram, this is what constitute our semi-formal notation for our architectural design. Okay. Then, when it comes to the block specification, we tried to elaborate on the ioctal kernel doc header to add all the missing information, with respect to the current kernel doc header, and with the goal, to provide a description of the behavior of ioctal, so that a test campaign could be derived from this specification, for the single block. Okay, you can see there is a to-do in the end because we didn't consider a set of ioctal commands. Okay, but this is okay. I mean, it's we can have some gap, so we know that that must be added. Okay. Then, okay, so this is the ioctal pre-existing code, and indeed, when it comes to block testing, we can use kernel self-test to define a comprehensive test campaign for the block VFS with respect to the ioctal scenario. Okay, and then when it comes to the architecture, when it comes to the integration test, and in this case we need to verify the software architectural model, we can leverage the runtime verification monitors. Okay, and this is very strong because if either the code is wrong or the model is wrong, so there will be an exception that is raised and the test fails. And now I will leave the scene to Daniel. So Daniel, please.
So hi, this is Daniel. So going in the other side of the equation here, right? So I just try to turn on my camera. I'm a visual person. This is me. So runtime verification is a lightweight, but yet rigorous form of verification method. And it's used in complement to other methods, right? And RV works by analyzing the trace of a system that is actually running and comparing it to a formal specification of the expected behavior of the system, right? So trying to put it in the Linux context. So in one side, we have the Linux realm, which we see as a set of traces, right? Tracing subsystem. In the other side, we have the formal realm, where we have a formal specification of the desired behavior of Linux. And runtime verification stands right in the middle. So in one side, it reads the system trace. In the other side, it reads the specification and tries to run the specification with the input from the trace, right? If everything is doing fine, the system might just run and nothing happens. If something not expected in the specification happens, we can take some reactions. For example, we can go to a fail-safe mode, or we can hit a warning, say, okay, this documentation is wrong. So, but seeing this technical bit, right, how do we fit it into this more, let's say, political or documentary or explanation side that is required for certification authorities, right? It's more the paper side, not in the code side. So the idea that Gabriele was explaining now is that we have a set of requirements. We will split it into blocks. We try to do analysis, create documentation, and explain how the system should run. For example, using UML sequence diagram, right? So the idea here is that with runtime verification, we could theoretically read this input from the diagrams, translate it into code that might run on Linux, verifying if the trace is matching with the documentation, right? So it will close the loop between the documentation and the documentation and the system, the actual implementation. And it might be useful for two things, right? First, to improve the documentation, to see if we are covering all the things that we expect, all the details of the specification in the all the details of the kernel in the specification, right? And we do this by showing that, okay, the specification is broken, it's broken, it's broken. It will reach a time in which the specification might stop being broken, it could stabilize, and then we can start pointing to problems in the kernel. So the idea, Gabriele came to me and told that, okay, parts of the system that we can describe, there is the runtime part that we use UML diagram, and you see it's just a sequence of events and states, and that can translate straight to a formal format. In this example, automata, and those who know me already know where I'm going to. So yes, in last years, people will know, because last years I've been trying to use automata to explain the behavior of the kernel, right? And I was able, not using this methodology, right, for trying to explain the properties of the branch RT, I was able to create a considerably large model, like with more than 9,000 states and 21,000 transitions, using some small specifications. So using it in a way that we could understand small specifications and build the big image of the system, and and how to integrate this into the practice of a kernel developer, making it code, making it easy to run. So before going to the code side, it's important to recall for many people here, or to explain to the people that was not here 1 or 2 years ago, that this idea of using automata to verify the runtime behavior of Linux is efficient. One of the questions that is often raised for the application of formal methods is, how much time does it take to verify a property or to verify the system? And here there's a paper I will post a link to this paper where I show that running an automata inside the kernel as code, C code, synchronously to the system, it is faster actually than tracing the same event to the trace buffer for later analysis. We have all the details on the paper, and I will put the link later. So that was more the research side. And the good thing is that this is getting practical. Earlier this year, I submitted the first version of what could be the runtime verification interface for the kernel. You have the link here, and it was welcomed by some key people. Steven, I'm targeting this as a complement of the trace interface inside the kernel. So back sent to Steven. Steven liked it. I had some good feedback from people like Peter Zilstra. So things seems to be feasible, right? And it's mostly this interface is built upon two pieces of software. And the first piece is the .2k, which is a tool that can translate these automata format in the GraphViz format. An automata using the GraphViz format, we can translate it into code, a C code that represents the same automata. And I also added some macro functions that can read that model code and enable it to run inside the kernel as native C code. And the only thing that is left for a developer is to connect one automata event or one UML diagram event to the kernel event that represents it. So it's just the instrumentation part. The patch set includes documentation that explains all these steps and at a good level. And so, once you have your model compiled and loaded into the system, you can load models on demand. You just go to the trace interface, like here, for example, syskernel tracing. I created an RV director there, and I can say things like, for example, in the second line here, I can say that I want to activate a reaction when something bad happens for this WIP monitor. I say, okay, please panic the system if an unexpected event happens on this WIP model, right? And to enable the monitoring of this model that would be hooked to the events and starts to run in the automata, you just enable echo WP enable monitor. So a very common way to do things in the tracing subsystem. And one thing that I also added is that the developer can watch the monitor running by, for example, enabling these trace points and reading them via ftrace or via BPF or via perf or anything you can hook to events. And that's the idea, to use monitors to transform documentation into C code, and they use it to verify if the documentation is correct and if the kernel is correct. There is a lot of information about it around. I have published some a summary of this research on Red Hat Research Quarterly magazine. It points to all the points that you might be interested to understand. A more heavy documentation, you see there are two academic papers here, one journal and a conference, and they have all the details of the implementation in the more, let's say, formal side. And finally, there's a link for a presentation I gave at the LC 2019. I think it was the last event I went in person. And it explains all the details of the formal verification we did. And yeah, and it's back to Gabriela.
Okay, so thank you, Daniel. So having talked about the real-time verification monitor, we can now go, to the last slide about the pain points and the next steps. Really. Okay, so communication diagrams, between subsystem and drivers. So this can be supported by static analysis tool of the code, and we have developed. Mobileye has developed a call tree tool in the context of ELISA, and this is public, and I can provide the reference to it. So this tool is able to support the generation of these static communication diagrams, okay? And the dynamic diagrams, so the baseline for them, only the baseline, that could be automatically generated by tracing the interfaces between subsystem once we have the communication diagrams. So basically, what we do, we stick traces to the interfaces between the subsystems, and then the dynamic trace log would be a sort of baseline of flow diagram. This is indeed, only a baseline. Okay, so that cannot be our flow diagram, because otherwise, if there are bugs in the code, we will never be able to spot them, because it will be an architecture automatically, generated based on the code, and this is wrong. Okay, so the idea is that we can have tools to generate baselines. However, it is absolutely mandatory to have a human review of the code and of the generated baseline, so that the model is the re-architecture model is created by human. Okay, and another pain point is indeed kernel doc headers, because if we say that the top level specification of drivers and subsystems, and anyway whatever is a unit, is written following the kernel doc headers, it is mandatory to expand these kernel doc headers so that the missing behavior is also reported in the headers itself, right? So it is a significant amount of work, really. However, so this is the idea, behind this model. Next step, so the first one is indeed to develop and refine the tools that would augment and support the generation of the software architecture models. Continue the development of the runtime verification interface. And then finally would be, to go high scale, trying to push the tools and engage with maintainers to also to push the models and the architectural description. Okay, so indeed, this can be done gradually, right? Starting from the subsystems that are more critical, but yeah, this would be the idea. And now I think we have it's questions and answers time. So.
So I do not see any questions in the chat. Does anybody else have questions they want to ask? Feel free to ask in the chat or unmute yourself and ask away. Okay, well, thank you ever so much for a very important and useful presentation. It's really interesting to see how we get Linux into places like that where we really need that safety. And it's a difficult problem. Thank you very much for being part of Plumbers.
Okay, so thank you very much, David, for hosting.
Yeah, thank you all. See you
Thank
around.
you. See you tomorrow.
Thank you. Bye-bye.
you.